Good afternoon to all. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome everyone to the National Conference on Mathematical Modeling with Differential Equations, Day 2, invited talk on infectious disease modeling. Dear participants, your active participation is important throughout the program. You can post your questions and comments in the chat box. Now, I take great pleasure to introduce our resource person, Dr. S. Minirani, Associate Professor of Mathematics, Department of Basic Sciences and Humanities, MIMS, Mumbai. Dr. S. Minirani graduated in Mathematics from Malabar Christian College, Calicut in 1997. She has secured first rank in MSc Physical Oceanography from Calicut University of Science and Technology in 1999. She has also done master degree in mathematics in St. Joseph College, Devagiri in 2006. She has completed her PhD in mathematics from NIT Calicut in 2015. Dr. Minirani has 13 years of teaching experience in various reputed institutions and 2 years of research experience in National Institute of Oceanography, Kochi. Currently, she is working as an associate professor in mathematics, Department of Basic Sciences and Humanities, NMIMS, Mumbai. She is the recipient of the following awards: Paper Award in National Meet of Research Scholars, IIT BHU in 2012. Outstanding Woman in Science in Venus International Woman Award 2018. IMRF Best Scientist Award in Mathematics in the 100th Conference of IMRF at Goa. Bharat Excellence Award in Mathematics Friendship Forum in 2019. She is a life member of various professional organizations and reviewer of Mathematical Reviews, American Mathematical Society. She has published many papers in reputed journals in the areas of fractal geometry, fixed point theory, graph theory, and oceanography. She is the author of the book Fractal Space, Introduction and Applications. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I once again welcome you, ma'am. Now I hand over the session to you, ma'am.
A very good afternoon to one and all. Can I start with my talk?
Yes, ma'am.
Yeah. A very good afternoon to one and all who are present here for the conference. So I would be actually sharing my knowledge on infectious disease modeling with you today. So let me start the session. Okay. First of all, I would like to thank the organizers, the PG and Research Center of Mathematics at DGCS College for inviting me, giving me an opportunity to be a part of this conference. Thank you, sir. And thank you, the organizers. Today I'm going to talk to you about the infectious disease modeling because, as you all know, it is a conference on mathematical modeling with differential equations. So you would have heard my introduction, which was given by sir. Thank you very much for that wonderful introduction, sir. But in that, you would not have noticed my area of interest as infectious disease modeling. So to start with, actually, I am a person who's currently learning, or is trying to work on. Actually, I have started learning infectious disease modeling and started developing interest in modeling using differential equations. And I would intend to work in this area. So this is also coming as one of my areas of interest, I should say, because it was not listed there. So as someone who has been working for so many years in this field, on the mathematical modeling field, so you can consider me as a beginner or else a learner stage only, not an expert. Okay. This is what I wanted to say, because I developed interest in this obviously because of this scenario that is going on worldwide now. And that is how I started learning this. And slowly, when I started learning and started working on it, I found that this field is quite interesting, and that is how I have what do you say started learning more, or else trying to learn more, or trying to listen to more talks on this modeling of infectious diseases, or else epidemic modeling. So as I always do for any of the presentations or else talk that I give, or else normally in lectures also I have a habit of this. So let us start with a quote uh, by George Box, which says that remember that all models are wrong. The practical question is, how wrong do they have to be, have to not be useful? So that means every model is useful in some way or the other. So it's about realizing how much wrong uh, are they not to be useful. So you try to understand that. So since our topic is infectious disease modeling, let us understand what is infectious disease. Because as mathematician, I have always felt that our challenge, especially, I don't know, I cannot generalize this also nowadays, because there are so many people, mathematicians, who are working in the application field. But to be frank, as a mathematician myself, I have always found it challenging uh, to understand all the terminologies with respect to the engineering field, or else with respect to the biological field, wherever it is going to be applied. So when it comes to the usage of terminologies in a particular field, where we are going to apply what we have learned, then it becomes a little bit difficult for me to explain it, because I feel like mathematics I can explain, or is the field which we have been learning and we have been quite familiar with for years, we are able to. And for us, most of the things are x and y always. But when it comes to actual application part, all these takes some terms, or else it represents something in that particular area. So even when I used to explain application problems to engineering students or technology classes, so I feel like understanding their terminologies and being quite familiar is one of the challenges that the mathematics teacher would be facing. Those who are teaching in the application field, or else I should say in the engineering or else technology to engineering or technology students. So let us understand the basic terminologies that we will be using throughout. So I think this is a common word, and nowadays almost all the terminologies that I'm going to explain may be familiar to you, also because of the prevailing situation that is now going on. So infectious disease, the definition is it's an illness due to some specific infectious agent. It can be virus, it can be a bacteria, it can be a protozoa, anything, any agent or its toxic products that arise through transmission of that agent or its products from an infected person, animal, or some reservoir to a susceptible host, either directly or indirectly through an intermediate plant or animal host, vector, or an inanimate environment. So it's this is what infectious disease is about. So it is an illness caused about by an infectious agent which is transmitted to others through some medium. Uh, so, so what is infectious disease epidemiology? So epidemiology means it's just the study of diseases and their determinants in the population. So it actually, epidemiology identifies a group of individuals in the population. So they are having the similar characteristics. They may be a particular age group, or else, some particular size or sex. It depends upon the study that you're carrying out, ignoring the uniqueness of individual members. So we are not actually studying the situation of by considering the properties or the uniqueness of each of the individual members, but we consider as a whole a group which is having a certain set of properties. Okay, it tries to determine whether the division of individuals into groups tells us something more that we could have learned by merely observing each individual separately. So we actively try to arrive at conclusions by studying a group of individuals. So definitely, our goal would be to understand or to analyze and understand, or else to describe some patterns of disease. Okay, in such groups. So when I'm talking about this dynamics, it can occur at different levels. It can be at micro level, that means within the host only. Meso means between the host, and macro between the populations. So between the population, so it can be of any level. When you are talking about epidemiology, your study can be carried out at any level. It depends upon the parameters that you have to consider. Because I remember when discussing about this COVID situation and the studies that was carried out at IIT Hyderabad, one of my friends who's working there, who's working in this field, he was saying like some of the the effect of the transmission through aerosols. They were studying about, and one very beautiful paper has come out, and he was saying like, see, in order to go to the what do you say, global level, lot of things has to be studied, like the aerodynamics and all. So it's about how much have should you go into, in which level do you want to carry out your experiments or else your study. So first of all, since you've been learning, I think you would have listen to so many mathematical modeling lectures, because the title itself is on mathematical modeling. So so for regarding epidemiology or else infectious disease modeling, why is it necessary that we need mathematical modeling? Because we have people all around, and how I see you, as you all know, to study any real situation, the first thing or the major studies are being carried out theoretically using the mathematical model. So mainly here we need to understand the competing risks of death. See, mainly when we are talking about diseases or any even infectious disease or else a disease otherwise, we are all worried about the death that has been caused about the diseases. Here also, the current situation also became alarming when the death rate started increasing. So always we try to limit the extent of infection through some control measures. Say for example, you can consider some vaccination, which we have been doing for many of the diseases, and then for some infectious diseases like this, quarantining and oral social distancing. These are the common terminologies which we use nowadays, so everybody knows this. So suppose you have some contact with an infectious person, then you do a contact tracing to know who all are in the possibility list for the next infections, etc. So the problem here is the data, the resources is always limited. When you carry out this mathematical modeling, the data is always limited, because normally it is considered to be unethical to use the data, because mostly the infectious disease that we are going to study or we are interested in would be the infectious diseases in human beings, and it's not quite ethical to use this data so publicly. So actually we must decide what is the optimal combination of the use of resources. In most of the cases, all these studies and all these assumptions or predictions are mostly done using the mathematical modeling, and then doing a calibration with the existing data, and trying to predict or project when this is going to end, and when would the peak appear, so that we need to know, we should know what are the precautionary measures that we should take, etc., etc. So actually the motivation lies in understanding the salient features of infection dynamics. So we are interested in understanding the infection dynamics. See, how does this spread? And our major interest also would be to forecast or predict the outcomes of this disease. Okay, in terms of demographics, then may country wise also, or else communities, we need to understand how it is spreading, and to understand its characteristics and how to control it. So these would be some of the points which I would say which would have led to the mathematical modeling of infectious diseases, because we need to understand the mechanism influencing the disease spread, and also link the individual scale clinical knowledge with the population scale patterns, because we need to study in cases of a pandemic like what is going on now. We need to know more about the population scale patterns that's happening. Then so we need to have a proper clear statement of our assumptions and hypotheses. That is more important before defining any model or developing any model. And using the mathematical analysis or the simulation, mainly the simulation studies are happening in order to do the forecasting or the predictions nowadays. And since you all are aware of many of the softwares that will help you to solve this and to simulate this. So also we will try to establish the relative importance of different processes and parameters to focus on the research part and also on the management part. Okay, so always we are trying to answer what if questions, actually, because real experiments are not possible in most of the cases, as you all know. So we need to do some simulation studies or what I say modeling studies only to arrive at conclusions, which can be tested, of course, using the existing data, but still mostly simulated studies are being done, as I've told. So you know that models are very simplified representations of complex systems, and you can actually increase the complexity of your model that you're going to define depending upon the conditions or the parameters that you need to consider. Okay, so if I'm saying quantitative predictions should be, I should say virtually impossible only. So exact predictions you cannot. So we will only be able to what do you say, predict it to the maximum extent possible. That is the only thing that can be guaranteed. So not only for this disease modeling, for in general for any modeling. So this, if I represent this mathematical modeling analysis and the numerics, it would be like this. So you have you make a model, then you have a model system. So you construct approximate theories, then you perform simulations, you have the simulation results and also your theoretical predictions. So you compare both, and then you try to improve the model. And in the same way, you have real system on which you can perform experiments. Case I'm saying infectious cases and performing real life experiments is not so easy. So in the same way, you compare it with the simulation results or the experiment results, and then you compare and try to understand where it has to be improved. Okay, so this model I have just taken for you. I think you would have seen this model in any of the mathematical modeling lectures. So how did it all start? Just to understand how did it all start. So it was actually in 1760 where Bernoulli formulated and solved a model for smallpox, and using his model, he evaluated the effectiveness of vaccination, actually, of healthy people against the smallpox virus. That was the one which was reported earlier in the history. So then Hammer in 1906 also, he formulated and analyzed a discrete time model to understand the recurrence of measles epidemics. And in 1911, Rose developed a differential equation model for malaria as a host vector disease, and he won the second Nobel Prize in medicine. And then it was Kermack and McKendrick in 1926 extended Ross model and obtained the epidemic threshold results. So these are a few of the historic results that you can see in the field of mathematical epidemiology. So these would be some of the key terms we will be using to describe the individuals. So when I'm saying susceptible, it means it's an uninfected group, but able to become infected if exposed. And infectious means already infected, and he's able to transmit the infection to other susceptible individuals. Immune means he's having, that individual who's having cell-mediated or humoral antibody protection against that infection. So diseased or clinical infection or clinically infected means it implies the presence of clinical signs of pathology, not necessarily not synonymous with infected, but there's some that symptoms are there. So latent infection or subclinical infection means the presence of infectious disease but absence of clinical disease. That means symptoms are not there. Now carrier means it implies a protracted infected state with shedding of infectious agent. That means carriers may be either deceased or a recovering person, or else a healthy person also. So some healthy person who's having that infectious agent inside, who has not developed symptom, also can be a carrier. Who's in the recovering stage can be, depends upon the disease that you are considering. Some of them have the infectious period during towards the end or at the recovery stage, whereas for some it's at the in the initial state. So these are the key time periods for an infectious disease. So latent period means It's the period immediately following exposure, when an individual is infected but he's not infectious. And the incubation period means it's the time between exposure and development of symptoms. So note that there is a difference between incubation period and latency period. A virus may or may not be dormant when an individual is in an exposed state. So there's some difference between latent and incubation period. Now, these are the relationship. See, it happens like this. If there's an infection happening, so he's in the incubation period, and then he moves to the latent period, and see, then he develops clinical disease. That means he develops symptoms, and that is how, see, from there, during the infectious period only, he gives it to the second patient, and then it continues, okay, as the time goes. These would be the words that you have been now quite familiar with. But what are exactly the difference between these? You would have heard epidemic, outbreak, endemic, pandemic. Pandemic now only we would have heard, but outbreak you would have heard earlier also. So what is the difference? A simple way to know the difference between an epidemic and a pandemic is to remember the word P, I should say. It's just like pandemic means you need it has a passport, so try to remember like that. It has a passport. That means it's an epidemic, or a pandemic means it's an epidemic that travels. So epidemic is just the occurrence of the cases or illness in a certain community or a region, whereas it goes to a very wide area, as it has happened now, crossing the international boundaries, usually affecting a larger number of population. Then it becomes a pandemic. So an epidemic is actively spreading. New cases of disease substantially exceed what is expected. So more broadly, it is used to describe any problem that is out of control. So epidemic is the illness that has been localized to a certain region, but the number of those infected in that region is significantly higher than the normal. For example, if we are considering the COVID-19 situation, it was limited to Wuhan in China, so it was an epidemic there. So the geographical spread has actually led or turned it to a pandemic. So endemics means they are the constant presence of some infectious agent or a disease at a specific location. Say, for example, malaria is an endemic in certain parts of Africa. And going one step further, an endemic can lead to an outbreak, and an outbreak can happen anywhere. So it's just an epidemic limited to localized, but increase in the incidence. So suddenly there is an increase to a huge number, but it's very localized. Okay, so these are the terminologies which we use to normally describe the infectious disease. Now we are coming to the basic compartmental deterministic models, SIS, SIR, or SCIR. What does it mean actually? See, in compartmental models, what you do is, it's a simplified mathematical modeling which has been used for modeling epidemiology, and the population is assigned to compartments within labels. So we assign the population to different compartments here. That is how the model name has come. And the people may progress between each of the compartments that you're considering, and you can increase the number of compartments depending upon whether you want to add more parameters to your study. So as and when the number of differential equations that is included also increases. See, the order of labels usually show the flow patterns, the order in which I say SIS. So each compartment refers to a particular state of the population. So the model are most often run with ordinary differential equations, as you all know, which are deterministic. You can also actually stochastic or random to it, random or stochastic models also. But then what happens is a little bit more. So the SI or SIS models, in SI you are thinking, you're considering your population to be never leaving the infectious state and have a long life infection. For example, herpes is a disease with lifelong infections. In SIS model, the people between the compartments susceptible, infected, and recovered, where infection does not confer immunity, or else we can say there is only a waning immunity. So So the individuals have repeatedly or they have reoccurring infections, and the infected individuals return to the susceptible stage. That is coming in your SIS model. And then SIR, the people move in the compartment of susceptible, infected, and recovered. That's what I was saying. And this can be modified always by adding your population turnover, or else the people in the recovery stage. See, all those compartments, depending upon the requirement of your study, you can keep on adding. And the people in R will move back to your susceptible again, because there is no immunity developed. So this can happen. Now SEIR is the one in which it's just a modification of SIR only, in which an exposed compartment before the. So because many diseases are also characterized by an incubation period, as I've told, between the exposure and the development of symptoms. So it is important to model the exposed state also explicitly, when there is a delay between the time at which the individual is infected and the time at which that individual becomes infectious. So in that case, SEIR model is appropriate. So say, for example, smallpox has an incubation period of 7 to 14 days. So you can still modify this now by adding mortality, by calling it as SIRM, wherein the death rate is also being considered. Then SEAIR, by adding asymptotic case also. Asymptomatic case also. Some cases there are people who are infectious, or else who are carriers actually without having any symptoms. So that can also be added as a compartment, and then you can actually improvise that model to SEAIR. So now talking about, so these are the basic deterministic models, and now we come to the reproductive rate. This would be one of the reproductive number, or the basic reproductive rate R naught, which you would have seen in the data also of COVID-19. So it is also called reproductive number. It means the average number of new infections caused by one infected individual. That means how many more people can one infected individual go out and infect. So that is called the reproductive number, or the basic reproduction rate. So we normally denote it using R naught. So in a population where it is less than 100% are susceptible, so the effective reproduction rate, or R effective, is defined as the proportion susceptible into R naught. R naught is the average number of new infections that is caused by one infected individual. So this is how it is. See, whenever R naught is greater than 1, the infection spreads, or else it becomes an epidemic. That means one infected person can go out and infect more than one person. So if R naught is 1, it means that infection remains constant. That's the case where endemic happens. And if R naught is less than 1, you say that the infection dies out. See, whenever R naught is greater than 1, it just creates some exponential growth. So the growth increases too much. And at some peak, the population gets immunity, and then slowly the number of susceptible declines. That is how you reach the peak, and then the decline happens. So without new supply of susceptibles, obviously the infection rate will or the infection will go down. Now you can have a case where some of the members or some of the population, some part of the population is already immune. So you have effective reproductive number, as I've told you. So initially you consider it as R naught only. When we come to the actual model and the simulation part, I'll explain it to you more. And it declines eventually to 1. Even though there are susceptible, there are not enough of them to maintain the effective reproductive number greater than 1. That means your epidemic slowly declines. And you would have also heard the case where about herd immunity. Herd immunity is the case where our effective reproductive number is less than 1. That means it's a situation where infection cannot spread easily because of the number of immune people in the population. So such a case is called the herd immunity. You can actually produce herd immunity. You can either reach it normally due to the normal immunity that has been developed in the human beings, or else through vaccination also. So somehow you are reducing the number of people going back to the susceptibles. So your is always, your R naught should be less than 1. Once you're able to keep it less than 1, then your infection dies out. It's no more an epidemic. So let us discuss more on the SIR epidemic model. As I told you, this is the way it is being explained, or it's been called. From susceptible, you move to the I compartment, and from there to R compartments. This is mainly your SIR, and we will be basically looking upon SIR and what do you say? Some improvisations done or some additions done to this model. So let us just understand the differential equation and the model as such. Let us start with the basic SIR model, in which you consider the force of infection is a constant. So you know that this you have 3 compartments here. So the rate at which people move from S to I is lambda, from I to R is gamma. So you have, since there are 3 states, you have 3 equations also. So ds by dt, it's the rate at which susceptibles are moving to infected. It's minus lambda into S, and di by dt is lambda S is plus and minus gamma I, and dr by dt is plus gamma of I. So this is how it is happening. So you are considering lambda as the constant force of infection and gamma as the recovery rate. So these are the standard terminologies that is being used. So using to build any of the transition model, we need to always quantify the transmission of people from susceptible to infected, which is actually the force of infection, and we divide the population into different compartments reflecting on their infection status, and in complex model potentially other characteristics also. But since these models are population based, all the individuals within the same compartment are subject to same hazards. So this is the assumption that we are actually making. So we start with a simple model. So we always stick to the homogeneity of the population. So whichever population we are considering, we consider that the entire set of population that we are considering for study is a homogeneous population. So whenever you are imagining a disease where you are either susceptible, infected, or recovered. See, when I'm studying about a population using this model, your entire population will be in any one of these compartments. So all those who are infected are infectious, and all those who are recovered are immune to the disease. This is how we consider in this basic model. So whenever I'm considering a model of this type, you just consider your entire population will be in any one of these 3 compartments. So now we can think of lambda as a force that is acting on susceptible people in the population, and it is working to turn them to infected people. So this is what lambda is doing actually. Even though it is not so realistic, this is the basic thing which you can understand. So in order to understand, we can just simulate this. I've used R programming only. So it is 10 raised to 6 here. So suppose you are initially thinking that one person is already infected. One person is infected, and so 10 raised to 6 is your initial population, and from there one has moved to the infectious case, and recovery is 0. So your constant force of infection is considered to be 0.2 per day, and the infection has an average duration of 10 days. So infections period is 10 days. So your gamma is 1 by 10, that's 0.1 day, and the time you're considering is for 60 days. So this is how I get the value if I try to simulate it. So this is how this S is your susceptible population. By within 60 days, here you can see the infected people. It reaches a peak, and then slowly it starts to decline. So in any epidemic basic model, if you draw this is going to be the pattern that you're getting. Somewhere you will get a peak, and then you will see a slow decline. Now, let us see, we considered a constant force of infection that would never happen actually in real case. So let us now try to understand this model with a dynamic force of infection. The force of infection changes over time. This is what we are assuming. Again, as I've told you, whenever we are starting with a model, there are n number of assumptions which you have to be very careful about while drawing conclusions, because these assumptions are required for you to do the studies, and at the end, when you're giving the results or the conclusion at the end, you need to consider this also. See, whenever we are modeling, this, we are considering the population to be homogeneous. That means everyone in the same compartment is subject to same hazards. This is the first thing that you assume. And the population is well mixed. That means all susceptible people have the same risk of getting infected, dependent on the number of infected people. And you consider that the population is closed. That is, there are no births or deaths. Actually, we are not considering that into study when I'm doing this. So these are the assumptions here. So you need to understand the assumptions before arriving at conclusions. Okay. So now, when I'm saying the force of infection is dynamic, that means it changes over time. See, at the beginning of an epidemic, there are no much infected people, you all know. So force of infection will be very, very small, as all of you know. But slowly, the epidemic starts to develop, or else it increases. The more and more people gets infected, and more people moves to the infectious compartment. So that means it drives your lambda. So now lambda is becoming dynamic. That is what we are considering here. So now we allow lambda to be a function of the variables. Okay. Let us assume that initially, on an average, a susceptible person has C contacts per day. Second, the proportion of those contacts are that are infectious is given by I by N. Okay, so this is called this is I by N, and N is the population size. So I by N is the fraction of population that is infected. So third, with every contact with an infectious person, the probability of infection is P. So this relates to the closeness of contact as well as how the infections, the disease is on an average. Now we put all these together and your lambda becomes P into C into I by N. That P into C is called your beta. So it is beta into I by N. So when this prevalence I is the only small proportion of the population, then your force of induction is also very small. And if we have highly connected population, that means in some densely populated city, we have high value of C. So your force of infection is higher here for the same disease in a rural setting. So as per the assumption, I'm equally likely to meet an infected person as an uninfected, but this may not be the case always, because why, the sick people normally have a habit of staying indoors as they are supposed to be. So I'm less likely to meet them. So that probabilistic term is always there. Okay. So the true value of C might be a little lower than your overall contact value. Okay. So now, it's very hard actually to measure what is the exact value it might be, especially in the beginning of the disease. So similarly, it's hard to measure the value of P also, that is the risk of infection or the contact, since the contacts vary so much, and then the duration and the intensity also varies over a single day. So for this reason, we don't try and estimate P and C directly. So instead, we are taking the product and calling it as beta, what do you say, the infection rate. This would be the what do you say, if you have been keeping an eye on the COVID-19 data, you would have seen the beta value and the gamma value, which is being calculated based on the existing data. So always your lambda now becomes a function of this beta into I by N. So it depends, it varies now. So you're considering it to be a varying, and this parameter can't be usually measured directly. You cannot directly measure this. Instead, we aim to choose a value for beta so that the model epidemic resembles the observed epidemic. This is all what we can do. So initially, to start with, it becomes very difficult to just give a value for this and then start with. What you do is you try to model it and in such a way that you compare it with the experimental results and try to get the best fit for this value. This is what we call calibration. So now when we that the total population means you are actually the entire total population, you are dividing into three compartments, S, I, and R. And this is your gamma is your recovery rate, and now lambda you are considering to be dynamic. So this is the simulation result. As in the earlier case, I'm starting with the 10 raised to 6 1% to be infected and considering beta as 1. And if I'm considering the infection has an average of 10 days again, so your gamma is 0.1. And I'll just study the epidemic or this disease for 60 days. So this is what I'm getting. Okay, so here you can see the peak is happening somewhere here after maybe around 18 days or something, and then slowly it declines and it comes near zero in 60 days. So now, since let us understand, like when I change these values of gamma and beta, or else by keeping gamma fixed and changing beta, what happens to the peak and how is peak varying? So if gamma is held at a constant of 0.1, which we have done in the previous two simulation also, we can see, and we increase the value of beta, then it leads to an earlier and higher peak of infected people. With a higher beta, the peak is also sharper, you can see. So these are the different cases of beta gamma combination. But gamma I have kept fixed to generate the results. You can see when beta is 0.2, this is how, see, the peak is happening. These are the number of days actually, 360 days. That means 1 year. And you can see somewhere around 125, 130 days it is happening. But the peak is very less. See, it's not it's not affecting more number of people. When I increase actually beta, that's your infection rate, as you call it. So you can see the peak is high, and here also it's very sharp. So with higher the beta, the peak is also sharper, and it's slow. It starts to decline again more quickly. You can see, so it starts to decline very fast. Beta of 0.1 actually does not give rise to an epidemic at all. So if we keep your beta as 0.2, you can see there is no peak or anything happening. That means it is not giving rise to an epidemic. So the number of susceptible infected and recovered people stays the same as in the beginning only. So now different recovery rates. So now let us change gamma and see what is happening. So different recovery rates affect the epidemic. I'm keeping beta as 1 throughout, and I'm changing gamma and seeing what happens. If beta is held as a constant at 1, the increasing value of gamma tends to lead to a later and lower peak of infected people and an earlier rise in the recovered curve. You can see it. So if people can stay infected for a longer time before recovering, that means if your gamma is 0.025, corresponding to an average duration of infection of 40 days. So the number of infected people stays high over a longer period and declines slowly. That means the epidemic flattens out. In contrast, if the recovery happens very quickly, that means gamma is 0.5, say for example here. So there is only a small peak in the prevalence of infection and the epidemic dies out very quickly. And there is no much height for this peak, you can see. If gamma is as large as 1, that means no epidemic takes place. So when you introduce just one infected case, there's no possibility of an epidemic happening. Now this is what we were talking about. Your R naught. R naught is given by beta by gamma. If I have to collect where beta is the average number of secondary infections per unit time, and gamma is the hazard rate of recovery from infection. Um, so this is also a case in which probability parameters are added so that you have increased the compartments actually. So this is how you calculate your R naught. This is an example. So R naught is given by beta by gamma. Now, okay. So effective reproductive number is the average number of secondary infections per infected case at a given point of an epidemic, and it takes into consideration the immunity part. So in a homogeneous population, R effective is given by the formula R naught into S by N, and it varies in the course of an epidemic. It decreases in proportion to the number of susceptible cases, and in the beginning you consider your S as your N only, and R effective as your R naught. So when it drops to 1, every infected case replaces with only one case, and hence the case declines. Okay, before coming to this, I need to also see another thing that you have to notice is the role of immunity in an SIR model. So when people go to R, they stay there, and this means the people are immune forever. So this might be okay for certain diseases like measles, but not like other diseases like influenza and all, where immunity wanes out over time, or the immune people move out of this and go back to the susceptible. Okay, so sometimes they may die of natural causes, and they may be replaced by newborns, so they also don't have any immunity. So when we think of these expectations, we see that SIR is a good fit for very special situations where population doesn't change and where the immunity is stable during the simulation period. uh, Now coming to the prevalence and incidence, see, let us understand here what is I. See, the number of infected people at any given point of time. In epidemiologic terms, it is the prevalence of infection. But there are many cases where epidemic data comes in the form of incidence. So let's understand the difference between these two epidemic quantity and what they mean in the modeling context. Imagine that in a tub of water, there is a faucet pouring water into the tub, and at the same time, there's an opening, sinkhole through which the water pours out. So we are looking at the case where overall water remains steady. So imagine the water in the tub represents the number of infected people in the population, and let's freeze that. Let's freeze the water flow for a moment. So we say that we see that what amount of water is in the tub at a given point of time. So the prevalence is that amount of water in the tub at any given point of time. And by contrast, incidence has to be stated with respect to an interval of time. Just like the total amount of water flowing into the tub in an hour, or the total number of cases that occur every week. So you have to actually say about incidence with respect to some time period. Prevalence means it's the value of I at a given point of time. Incidence means it's number of new cases over a given duration. So that's the actual difference between prevalence and incidence. So both are giving you the amount of infected cases only. One is at a given point of time, whereas the other is the new cases that has been added during the duration of your study. So this is what prevalence is. Prevalence is the number of infected cases at a given point, whereas incidence is the number of new cases in an interval, for example, for a week. So in order to just study the effective reproduction number, so we have chosen a daily infection rate of 0.4 and a daily recovery rate of 0.1 to get an R0 of 4. So modeling this epidemic over the course of 3 months, this is what we see. You can see that the peak is happening around 15 days if we are considering the duration of 100 days study. So you can see it's almost the same pattern that has been given like S. Is it the same pattern that has been taken by the effective reproduction number? Because as the susceptible reduces and it dies out, so this is how it happens. So how does R effect vary over the course of an epidemic? And what do you notice about the connection between the change in the effective reproductive number and the epidemic curve over time? Or in relation to the effective reproductive number, when does the epidemic peak and start to decline? These would be the questions that would be having with respect to the effective reproductive number. So, you know that as I've told you, the effective reproductive number is always highest when everyone is susceptible. That is how you start with. You assume that it is your reproductive number or not. At this point, every infected case causes an average of 4 secondary infections. Okay, for the example that I have explained just now. So, over the course of the epidemic, it declines in the proportion to, see here. See, from 4 it starts, and it slowly starts declining. And you can see in proportion to your susceptibility only. So that's why you're getting the nature of the graph as the same. So you can see the susceptible graph is similar to what it is. So the shape is the same. So you start with maximum of 4. That was your R0 that you've chosen. So your R0 you've chosen to be 4. And so you start with your effective reproduction number also as 4. And then you slowly see that it declines. And here in the example, we have considered it for 50 days, and it goes down to 1 in 50 days. That means in 50 days when your peak happens, see from there onwards it start fading. So from 1, and as effective reproduction number decreases beyond or further below 1, the epidemic prevalence goes to decline. That is exactly what you can see after 50 days. See, it's declining only. This is your I curve. So after a peak at 50 days, at the 50 days it comes to 1. So always it is like that. Your effective reproductive number, then it goes below 1 and slowly it dies out. So once the epidemic reaches the point where every infected case cannot cause at least one more infected case, that's the meaning of saying that R effective or else effective reproduction number is less than 1. So that means the epidemic cannot sustain now, and it comes to an end. Sorry. Now, here, as when we have modeled it earlier, we have not considered the population turnover. That is what I was saying. In SIR, when we considered the case where it was having constant force of infection and also then a dynamic force of infection. That is the real case. But we didn't consider the birth and death that is happening. So when I'm actually adding you are actually increasing the complexity here one by one. See, I am adding the birth. This is your birth rate V, and this is your death rate mu. So death can happen in any of these compartments. The susceptible group can also die. The infected people also can die. The recovered people also, maybe due to some other natural causes. So that's the rate at which actually the population is decreasing. So your differential equation accordingly changes. So now there is a birth that is to be considered. So it is minus beta, that is your lambda. Lambda is nothing but beta into I by n. So minus beta I by n into S minus mu S, because this is also going out from this population, and plus this is the entry, plus B into total number. Okay. Then di by dt, again you have beta I by n into S, then two rate that is going out, gamma and mu. So it is minus gamma into I minus mu into I, and then in R also it's gamma I minus mu R. So this is how I have modified this IR model to consider the population turnover also, the births and deaths. Okay, here we are running the model for a 400 year period. First, only plotting the number of infected people only for the course of 1 year. Okay, so this is the after the introduction of the infected case. So it's the epidemic curve in the first year after it. So these are the values that we have considered for simulation. So when I'm plotting the over several generations, that means long-term epidemic curve if I study. So over several generations, if I'm doing the study, like this is the time period over 400 years. So you can see like sharp epidemic cycles. So the epidemics will occur repeatedly over time, but you can see the peak is actually becoming smaller and smaller, and it eventually disappears. This pattern occurs because the disease has much shorter duration than the human population turnover. So once an epidemic has spread throughout the population and depleted the susceptible pool, it takes a long time for the susceptible to replenish through births. And this is why if we see these deep troughs see deep and long troughs in the around 70 years until the second epidemic between the epidemics that you can see. So this is the same graph only. So modeling the same population over 1 year, this is what we see, the prevalence of infection, susceptibility and recovery over the time. So the same study we have drawn it for. So this is, I told you, R effective will have the same pattern of your susceptible, because as the susceptible population declines, that is how the pattern of R effective also will be the same. Now, since now we have considered how the model has been changing when the vaccination is added, or some what do you say, Let us discuss one simple vaccination model also, because just to conclude. So what happens here is, in your initial condition at time t equal to 0, you assume that your susceptible is 1 minus p into n minus 1. So that means some part of your population is actually immune to the disease. Okay, so that is the case that you are happening. Now, another question that you will be having is, whenever I'm considering the case where vaccination is also included, does everyone in the population need to be vaccinated in order to prevent an epidemic? And when you do this simulation studies, what do you observe if you model the infectious dynamics with different values of P? So when I'm modeling the disease where beta is again 0.4 days, gamma is 0.1 days, and vaccine coverage about 0.5, that means 50%. See, everyone in the population need not be vaccinated in order to prevent an epidemic. So it depends upon your condition actually. So if P equals to 0.75 or higher, no epidemic occurs. So that means 75% is the critical vaccination or the herd immunity threshold. So the herd immunity describes for these conditions, I'm saying, when I have modeled it using these beta and gamma, so it depends upon your beta and gamma values for which you decide your P. That means how much percentage of your population needs to be vaccinated so that it doesn't become an epidemic. So the herd immunity, as I've told you, describes a phenomena in which there is sufficient immunity in the population. It can be either through vaccination or else naturally developed immunity. So not everyone need to be vaccinated. So when I increase the vaccine coverage to 75%, this is what I got with these values of beta and gamma. So you can see that. So in this way, if you are able to identify your beta and gamma for your disease, what you can do is you can actually identify what is your vaccination threshold or herd immunity threshold. The meaning is how many percentage of your what percentage of your population has to be covered using vaccine. So this is how I calculate it in mathematical modeling terms. Herd immunity means it's same as saying that your R effective should be less than 1. As I've told you, when your effective reproductive number is less than 1, then the epidemic dies out. So that means you can use this to derive your herd immunity threshold. So R effective should be equal to your R naught into S by N. And so you have it is actually, if you're considering that much population, a particular percentage of population to be immune, so R naught into 1 minus P, you can equate both, and you get that P as 1 minus 1 by R naught. So we can calculate R naught by dividing beta by R naught is given by the equation beta by gamma. So you can have a case where waning immunity, see, the immunity dies out after a certain time, and then the recovered people slowly moves with the rate of sigma to back to the susceptible population. So what do you observe about the infection dynamics? So how does this compare to the model with the population turnover? So when you compare this, when modeling slow waning of immunity, we observe that the same epidemic patterns as when we model an acute disease in a population with slow turnover, spikes of epidemics alternating with long deep troughs reflected in the cycle of susceptibility and recovery, but eventually it dies out. However, with an average duration of the immunity of 30 years, the rate of waning is still quicker than human population turnover. So therefore, there is a time between epidemics, and that is actually becoming shorter because of this. So while in the population turnover example, the source of new susceptible were births, here the people losing their immunity. So instead of birth, here people from recovered compartment is moving back to the susceptible. That is your that is not by birth, but due to the waning immunity, they travel back. So what implications does it have for the vaccination programs? Due to waning of vaccine-induced immunity, one of vaccination of the population is not sufficient. One-time vaccination may not be sufficient to prevent an epidemic in the future. So the model predicts that a smaller epidemic occurring about 10 years after vaccination. So it might be necessary to deliver a second booster vaccine also within that time period to maintain a sufficient herd immunity in the population. And also, it is important to note that this model makes many simplifying assumptions and ignores the fact that I told you, whenever we are doing this modeling, a lot of assumptions goes back as a homogeneous population, as you know that that's not correct or the same in the real case. So based on this alone, we cannot draw results. So do I have time? So I'll take only 5 more minutes to quickly just show my results. So when I change this sigma to reflect the fast waning immunity, what happens? See, you can see what difference do you observe in the infection dynamics if I choose my waning immunity to be much faster. The outcome under these assumptions is very similar to what we have observed earlier. See, the infection quickly reaches an endemic equilibrium with an effective reproduction number staying stable, and because just as in the population, the pool of susceptible is continually being replenished by these people who are coming back. See, from both the examples that we have studied, we can see that the waning immunity acts in the similar way as the birth rate. That's birth rate also, it's the same case. You get a new population added to the susceptible with no immunity. So if you change the initial state values, what changes do you see in the infection dynamics? See, you can see that the system eventually stabilizes. It's the same values as in the previous example, where we assume that the single infected case was introduced. So if we are modeling an endemic infection with a combination of parameters that leads to continuous addition of new susceptible and reaches an endemic equilibrium, the initial number in the compartments will start off. It does not affect with what number we have started off, does not affect the endemic prevalence actually. That is being reached. So this is in contrast to what we saw in the previous case, where changing the initial proportion of the population that was susceptible determine whether an epidemic would occur or not. So okay, this is one task which I would like the participants to carry out. The task is like this: a new respiratory virus has begun circulating in another country. So for epidemiologic investigations, so we are giving some data and write a model, and you answer these questions. If a vaccine conferring all or nothing immunity with 80% effectiveness becomes available before an epidemic begins in your own country, what is the minimum coverage of this vaccine? What is the minimum coverage or the threshold value that so that you can prevent it as an epidemic? See, these are the data given to you. An infected individual go through the incubation period, which lasts on an average of 4 days. So during this time, the individual are not infectious and do not have any excess mortality risk also. So all infected individuals eventually develop symptoms, and the mean duration of symptoms before either recovery or death is 5 days. And symptomatic individuals are infectious, as well as they are having 3% case of fatality rate also. That also needs to be included. So you can model it using these parameters. And in the source country, the peak prevalence was observed to be 8% of the population. That means the maximum number of symptomatic people during the epidemic. And assume that the source country and your country are epidemiologically equivalent. So in this case, you need to develop your own model. This was a task. I don't have much time, otherwise I would have explained it in detail. Those who are interested can write to me. I can give you this task and you can do this modeling and then do the simulation and give me the results. So in the same way, let us have the same way we have begun the talk. Let us end the talk also using a famous quote by listening to Albert Einstein. Quote by the formulation of a problem is often more essential than its solution, which may be merely a matter of mathematical or experimental skills. That's true. See, modeling it properly is more important. That, see, for solutions you have n number of numerical techniques. So all the simulations what I have carried out, and I've done my studies using R only. So these are the some of the references. Very few references only I have included. So basically, sorry, I have based it on the infectious disease modeling and the SAR model by what do you say, John Hopkins University. Their course only I have followed in studying actually. So these are some of the further reading that you can do. And thank you. And now it's time to take the questions.
Thank you, ma'am, for your wonderful session.
So I have exceeded the time. So sorry for that.
Questions? Sir, any questions, sir?
I have exceeded the time limit. Sorry, first of all.
No problem, ma'am. Ma'am, where is our question, ma'am?
See, R naught less than 1 means it's not negative. It's it's less than 1.
Less than 1 lies in between 0 to 1.
Yeah.
Sir, any other question, sir?
Okay, sir.
Ma'am, I think no more questions, ma'am.
Thank you so much. Thank you
Thank you,
so
ma'am.
much, sir, for giving me an opportunity. I had to rush through a few of my results because of lack of time. Sorry for that organizing part. And thank you very much for giving me an opportunity. Thank you, organizers.
Thank you, ma'am.
So, can I leave the meeting?
Yeah, yes, ma'am.
Thank you.
I'm very grateful and honored to propose the formal vote of thanks on behalf of PG and Research Department of DJ Vaishnav College to all who spared their valuable time. I would like to thank our distinguished resource person, Dr. S. Minirani, Associate Professor of Mathematics, Department of Basic Sciences and Humanities, NMIMS, Mumbai, for an excellent presentation and making this session a very meaningful and interesting. Once again, I thank you, ma'am. Our next session is paper presentation. I request the participants to follow the order. First, Dr. T. N. Mishra. Second, Mr. Agmal Rasa. Third, Ms. V. Batmavati. Fourth, Dr. Hemavati Patel. Fifth, Ms. Aishwarya S. Sasidhar. We will meet at 3:30 p.m. Thank you. முடிச்சுட்டு வெளியே போனாங்கன்னா உள்ள வராங்க சார். ஓகே சார். I welcome everyone to the paper presentation session. Today, our chairperson, Dr. S. Minirani, Associate Professor of Mathematics, Department of Basic Sciences and Humanities, NMIMS, Mumbai. I welcome once again you, ma'am. Paper presenters, make sure that your PPT presentation will not be more than 8 minutes of time duration. After your presentation, there will be a question answer session for each paper presentation. Ma'am, do you want to give any instruction, ma'am, to the paper presenter?
Sir, you have already read out, no? Like each presentation should be 8 minutes.
8
So
minutes.
the first 8 minutes they can use for presentation and the 2 minutes for question.
Okay.
Can we go like that?
Yes, ma'am.
So we'll
Yes,
switch off one candidate and then go to the next.
Yes, ma'am.
Yeah,
Okay.
you will be reading out the names, no?
Yes, ma'am. Now I will call, ma'am. Now
Yeah.
I invite Miss B. Padmavati to present a paper. Padmavati, ma'am.
Can you?
Yes, ma'am. Share your screen, ma'am. Your screen not visible, ma'am.
So now is it visible, sir?
Yes, ma'am. Yes, ma'am. Now visible.
Okay. Shall I start, sir?
No, ma'am. First open your PPT, ma'am. It's not visible.
Just wait.
You're sharing your windows only.
Is it?
Okay. A slideshow, ma'am. Full view and slideshow. Full view.
Full.
Press F5, ma'am, for slideshow or slides.
Sir, one second. Full view, sir.
But two. Okay. Okay, ma'am. Now you can continue.
Okay, sir.
Okay, ma'am. You can continue.
Okay. Shall I start, sir? Okay.
Okay, ma'am.
Good afternoon to everyone. I am V. Padmavati, working as an Assistant Professor of Mathematics in Jairam Arts and Science College, Salem. I am doing my thesis under the guidance of Dr. Alageshan and Dr. Magesh. It's my pleasure to present an article. My presentation is about application of various numerical and analytical techniques to solve Fittag-Negmo equation. Let's see the presentation. The pivotal object of this current study is applied to Q homotopy analysis transform method in fractional Fittag-Negmo equation, and the result is identified in convergence series. The mentioned example is elucidated dominantly and compared with FRDTM, RPSM, and FNDM solutions. Introduction. Calculus of fractional order is pretty antique in mathematics. Fractional derivatives were debuted in 1695 as in the question of the extension of meaning. Derivatives and the integrals of arbitrary order offered more factual models of the real world phenomenon. The problems relating to applications of fractional calculus are located in various connected branches of science, engineering, finance, nanotechnology, electrodynamics, many other fields. The analytical and numerical solution of fractional partial differential equation play a key role in describing the characters of nonlinear problems that arise in daily life. A general model of reaction diffusion equation dou power alpha u by dou t power alpha equal to lambda into dou square u by dou x square plus f of u. Then alpha lies between 0 and less than or equal to 1, t greater than 0, x belongs to R, where lambda is the diffusion coefficient and f of u is a nonlinear function representing reaction kinetics. In 1937, Fisher proposed a model for the temporal and spatial propagation of a viral gene in an infinite medium called Fisher equation. It is interesting to observe that for f of u equal to mu into u of x comma t, 1 minus u of x comma t in equation 1, dou power alpha u by dou t power alpha equal to lambda lambda into dou square u by dou x square plus mu into u of x comma t 1 minus u of x comma t, which is basically the logistic equation and the conjunction of diffusion equation with the diffusion factor lambda and birth rate mu. Here, u of x comma t specifies the state evolution over the spatial temporal domain characterized by the coordinates x comma t respectively. If we set f of u equal to u of x comma t 1 minus u of x comma t u of x comma t minus mu in equation 1, give rise to the time fractional Fittag-Negimo equation, which is an important nonlinear reaction diffusion equation and applied to model the transmission of nerve impulses, also used in biology and the area of population genetics in circuit theory. The next, for this Fittag equation, I have applied the following methods. They are QHATM, that means Q homotopy analysis transform method. The second one, FRDTM, fractional reduced differential transform method. RPSM, residual power series method. FNDM, fractional natural decomposition method. I have discussed the method with a suitable example. For this Fittag equation, first one, Q homotopy analysis transform method. The proposed method is coupling of the homotopy analysis method and the Laplace transform method. The main advantage of this proposed method is its capability of combining two powerful methods for obtaining rapid convergence series. The equation. Homotopy analysis transform method basically illustrates how the Laplace transform can be used to approximate the solution of the equation by manipulating the homotopy analysis method. QHATM is a modified technique of HAM, that means a homotopy analysis method. It does not necessitate linearization, perturbation, or discretization, and in addition, it will reduce vast mathematical computations and it free from obtaining difficult physical parameters and polynomials. The second method is FRDTM, that means fractional reduced differential transform method. The central benefit of FRDTM is that it can solve different classes of linear and nonlinear partial fractional differential equation in high dimensions. The most distinct aspect of this method is that no prescribed assumptions are required and the huge computational exertion is reduced and round of errors. Third one, the RPSM, residual power series method. The residual power series method developed by RQ is a novel technique for finding the analytic Taylor series solution of the system of linear and non-linear ODEs and PDEs. The residual power series technique supplies the approximate analytical solution of the problem. A truncated series formed using residual error concept along with given initial condition. Then finally, FNDM, fractional natural decomposition method. The fractional natural decomposition method is a combination of natural transform method and the adamant decomposition method. The nonlinear term can easily be handled with the help of adamant polynomials, which is considered to be a clear advantage of this technique over the decomposition method. I have discussed the method with a suitable example. I have the example is consider the time fractional Fittag-Negimo equation of arbitrary order dt power alpha u of x comma t equal to dx square u of x comma t plus u of x comma t into 1 minus u of x comma t u of x comma t minus a. Then alpha lies between 0 and 1, a greater than 0, x belongs to R, t greater than 0, subject to the initial condition u of x comma 0 equal to 1 by 1 plus e power x by root 6 the whole square. I have arrived the solution for QHATM is u of x comma t equal to 1 by 1 plus e power x by root 6 the whole square minus h t power alpha by gamma of alpha plus 1, 5 minus 6a e power x by root 6 plus 3 minus 15a e power 2x by root 6 plus 3 minus 12a e power 3x by root 6 minus 2 minus 3a e power 4x by root 6 divided by 3 into 1 plus e power x by root 6 the whole power 6 minus h into n plus h t power alpha divided by 3 into gamma of alpha plus 1, 5 minus 6a e power x by root 6 plus 3 minus 15a e power 2x by root 6 plus 3 minus 12a e power 3x by root 6 minus 2 minus 3a e power 4x by root 6 divided by 1 plus e power x by root 6 the whole power 6, like this. Then the FRDTM solution for Fn equation is u of x comma t equal to 1 by 1 plus e power x by root 6 the whole square minus 5 minus 6a e power x by root 6 plus 3 minus 15a e power 2x by root 6 plus 3 minus 12a e power 3x by root 6 plus 2 minus 3a e power 4x by root 6 divided by 3 into gamma of alpha plus 1 1 plus e power x by root 6 the whole power 6 into t power alpha plus etc. Then the RPSM solution for this Fn equation is u of x comma t equal to 1 by 1 plus e power x by root 6 the whole square minus 5 minus 6a e power x by root 6 plus 3 minus 15a e power 2x by root 6 plus 3 minus 12a e power 3x by root 6 plus 2 minus 3a e power 4x by root 6 divided by 3 into gamma of alpha plus 1 1 plus e power x by root 6 the whole power 6 into t power alpha plus etc. Then FNDM solution is
Ma'am,
u of x comma.
ma'am,
Sir,
out of timing, ma'am. Already 8 minutes more. So
and
try to finish.
finally
Okay, ma'am.
we
Conclude.
conclude. I conclude that, sir. Finally, we conclude that QHATM is highly coherent and it can be employed to examine. Hence, with the comparison of FRDTM, RPSM, and FNDM, the QHATM is the most appropriate method to find the solution for complex phenomenon. Thank you. Sir?
Yes. Ma'am, questions, ma'am?
Yeah. Is the participants having any questions to ask? You can type it in your chat box. I'm not able
Yes, ma'am.
to
Okay,
see.
I'm saying, ma'am.
So I would like to ask you a few questions. See,
Okay.
you have fixed the initial condition, no? Are you able to hear me?
Yes, ma'am. I'll fix the initial condition, ma'am.
Yeah, how did you fix it? Like, why did you fix it to that value?
Ma'am?
You fixed it to some function, exponential.
Initial condition. Then it's a differential equation, ma'am.
Huh?
I'm sorry, I can't understand, ma'am. U of x comma t equal to 1 by 1 plus e power x by root 6 the whole square. Yes,
so this
ma'am.
is your problem. This is your Fn equation problem with this initial condition.
Yes, ma'am.
So this is throughout for all the, see, whenever you consider Fn equation, this is going to be your initial condition.
Ma'am, in this problem, I'll check the initial condition u of x comma 0 equal to in case of 1 by 1 plus e power x by root 6 the whole square, ma'am. Otherwise, I'll give another more initial conditions. I'll take them, ma'am.
So why have you fixed it so? That's what I'm asking. You randomly chose an initial condition?
No, ma'am.
So you told me in different situation you take different initial conditions.
Ma'am? No, ma'am. No, ma'am. No, ma'am. That's.
Can you please explain?
Yes, ma'am. I'll take a different initial condition. The ratios, ma'am. Solution. I'll take that initial. Ma'am?
Yes. We are not able to hear you actually. Sir, are you able to hear Ms. Padma?
Yes, ma'am. Yes, ma'am. Audible. Yes, ma'am. Yes, ma'am. Audible, ma'am.
Audible? Okay.
But Padmavati ma'am having some network issue, ma'am.
That's right.
Yes, ma'am. Yes.
Okay, then we'll have to go to the next person because unnecessarily we are wasting time.
Okay, ma'am. Okay, ma'am.
Yeah.
Now I invite Dr. Hemavati Patel to present a paper. Ma'am, share your screen, ma'am. Your screen not visible, ma'am. Hemavati, ma'am.
Yes, okay, sir.
Okay.
Is it okay, sir, now?
No, ma'am. Your
Okay.
screen not visible. Yes, ma'am.
It's coming now, sir?
Okay, ma'am. Now open your slide, ma'am. The screen is visible, but not.
Urusha, madam?
No, ma'am. No, no. Ma'am, choose entire window and select PPT, ma'am.
Sure.
Yes. Now
Is it
slide show.
visible, sir?
Visible, visible.
Okay.
Slide show. Okay, ma'am. Okay, ma'am. Now it's fine. You can continue,
Good
ma'am.
evening to
Okay.
all of you, sir.
Yes, ma'am. You
So
can continue
myself,
now.
okay. Good evening to all of you. So myself, Dr. Hemavati Patil, Assistant Professor of Mathematics, Government Associate College, Manhali, District Bidar, Karnataka. So in today's session, I am going to present my paper as a heat and mass transfer of a viscous fluid in a vertical channel. So in this paper, I have studied the behavior of nanofluids in a vertical, but is investigated analytically in a vertical channel for isothermal boundary conditions with one region filled with nanofluid and the another region with viscous fluid. Separate solutions for each fluid is in each region is obtained, and these solutions are matched at the interface using suitable matching conditions. Continuity of velocity, shear stress, temperature, and heat flux is assumed at the interface. The transform dimensionless governing equations are solved analytically using regular perturbation method and investigated with 5 types of nanofluids for different values of Grashof number with a range of 1 to 20 and the Brinkman number with a range of 0 to 1 and solid volume fraction parameter with a range of 0 to zero point 0.2 are carried out. So it is found that the Grashof and Brinkman numbers are promoted the flow field, whereas solid volume fraction denotes the flow in the region of a nanofluid under the study. So here, so I have a brief introduction about this nanofluid because so in this region I have used two fluids. One is nanofluid and another is the viscous fluid. So just I'll give brief introduction about the nanofluid. So because of increment in energy price, heat transfer management is important in energy system. Recently, nanofluid technology is planned and studied by some researcher experimentally or numerically in order to enhance the process. The nanofluid can be applied to engineering problems such as heat exchangers, cooling of electronic equipments, and chemical process. In most of the studies, it is assumed that nanofluid treat as the common pure fluid. So this is the mathematical formulation. So in this so we have used this is two immiscible fluids in a vertical channel between the this is first region is occupied with the nanofluid in the region minus H2 0 and the second region is occupied with the viscous fluid between the region 0 and H. So here the nanofluid having the density of rho NF and the viscosity mu NF, thermal conductivity KNF and thermal expansion coefficient beta NF. Similarly, the region 0 to H, so this is the positive region, is occupied by the viscous fluid having the fluid density rho f, the viscosity mu f, the thermal conductivity kf, and the thermal expansion coefficient beta f. The flow in all three regions is assumed to be compressible, incompressible, and fully developed. So this is the physical. This is the physical configuration of this problem. So here we have two fluids. One is the nanofluid, and the second region is filled with the viscous fluid. And the walls are at different temperatures. So first wall is at left wall is at the temperature TW1, and the right wall is at the temperature TW2. So these are the basic equations we are using here. So in the first region, we have taken, this is non-linear differential equations, mu nf d2u1 by dy square plus rho nf g beta nf t1 minus tw2 minus rho p by rho x is equals to 0. And second equation is knf d2 t1 by dy square plus mu nf du1 by dy whole square is equals to 0. And second region is filled with the viscous fluid. No? So according to that, I have taken here mu f into d2u2 by dy square plus rho f g beta f t2 minus tw2 minus rho p by rho x is equals to 0. And next equation is kf. So this is the velocity equation. This is the temperature equation. So that is kf d2 t1 by dy square plus mu f. Sorry, it is not here. It should be t2. It is because it is the second region. No? It is filled with the temperature T2. It is. So plus mu f du2 by dy whole square is equals to 0. So the for this we have some boundary and interface conditions. Boundary conditions are on the both boundaries, and interface also we have one condition. So that is velocity u1 at minus h is 0, and velocity at h, that is u2 is 0, and u1 is 0 is equals to u2 0, and at the interface here, at the interface these two conditions we have here, mu nf du1 by dy is at 0 is equals to mu f du2 by dy is equals to 0, because here one region is filled with nanofluid and the other region is filled with the viscous fluid. So they are equal at the interface. So here also these two are equal here. Similarly, these are the boundary interface conditions for the temperatures. So these are the constants, these are the relations we are using to transfer this equation into non-dimensional forms. Now substituting all these to transform the above equations into dimensionless forms, we introduce the following non-dimensional parameters here. So these are the dimensionless parameters. After substituting these in previous equations, in equation 1 to 8, and after simplifying, we get these non-dimensionalized equations in the region 1. So it is d2u1 by dy square plus gr. Here gr is the Vaishnav number into a theta 1. A is the constant here. So we have some equation for this, and plus p into 1 minus 5 whole raised to 2.5 is equals to 0. And the next equation is, so this is the velocity equation, this one is the temperature equation. So it is d2 theta 1 by dy square plus br is the Brinkmann number, into b into du1 by dy whole square is equals to 0. This is in the region A 1, and for second region we have the same equations again. So that is d2u2 by dy square plus gr theta 2, here it is, plus p is equals to 0, and d2 theta 2 by dy square plus br into du2 by dy whole square is equals to 0. So next solutions. To solve these non-linear differential equations, we have used the method of perturbation method. So here in this perturbation method, first we define here u1 ui at y is equals to ui0 y plus br ui1 y plus br whole square ui 2y, etc. Similarly for temperature equation also we have same thing, theta I at y is equals to theta I0 y plus br theta I1 at y plus br square at theta I2 at y, etc. So this we can call it as a perturbation method. So here we compare the zeroth order equation, first order equation, and second order equation on both the sides, and we get these equations here. So that is, so these are the zeroth order equations. After using perturbation method, we got these equations for this region 1 and region 2. Similarly, by comparing the first order equations on both sides. First order means here the powers of Br is to 1 on both sides. We can get these equations. So these are all first order equations for region 1 and region 2. And solving these equations will get the solutions. So this is the thermophysical property of pure water and various types of nanoparticles. Because in this problem, I used 5 different nanoparticles here. Because one region is filled with the nanoparticles, that is nanofluid, and another region is filled with the viscous fluid. So for a nanoparticle, we have used 5 different nanoparticles here. So first one is pure water, second one is silver, copper, diamond, silicon oxide, titanium oxide. We use these 5 different nanoparticles for this problem. So next is the results and discussions. So here this figure 2 shows the velocity profile for different values of Grashof number. So here, in this we can see that here as the Grashof number increases, the velocity profile increases, and at the middle of the region it is maximum, and it ends both it is equals to 0 here. So that is, it shows that here, so in both figure 2 and figure 3 shows the velocity and temperature profiles for different values of Grashof numbers. Considering copper as a nanoparticle here, for this we have taken copper as a nanoparticle and water as a base fluid. And this figure shows that Grashof number increases both the velocity and temperature profiles, and they are enhanced in the both the regions. The optimal velocity is observed in the middle of the channel, and one can justify this result because Grashof number is greater than 0 is buoyancy assisting flow which supports the motion. The Grashof number acts as a driving force in the momentum equation. The velocity or velocity gradient increases, and therefore the effect of dissipation increases, which results in the enhancement of temperature field also. The effect of a Grashof number on the flow field is a classical result for single fluid flowing in a vertical channel. The same nature is also observed for 3 immiscible fluids flowing in a vertical channel also. And the next one is here, this figure 4 and 5. Figure 4 and 5 shows that the effect of a Brinkmann number on the velocity and temperature fields. So for Brinkmann number greater than 0 and using water
I'm
based
taking more than 8 minutes, ma'am.
Okay,
Can
sir.
you give conclusion part, ma'am?
Okay. So next one is here. So these two are the figures for different nanoparticles. We have taken here different nanoparticles, and for that also we have calculated velocity and temperature. So last one is conclusion. So this is the analytical studies were carried out to understand the flow nature of the nanofluid and viscous fluid. The Tiwari and Das model was used to define the nanofluid here. The regular perturbation method was opted to solve the nonlinear coupled equations in all the 3 regions using Brinkmann number as a perturbation parameter. And it was concluded that as the Grashof number and Brinkmann number increases, the flow is promoted in both the regions, whereas the solid volume fraction denotes the flow motion. And we can also observe that here, optimal flow was observed using silicon oxide as a nanoparticle, and the minimal flow was observed as diamond as a nanoparticle, keeping water as the base fluid. However, there was no distinguish between, there is no any distinguish between the nanoparticles. So this is all about my presentation. Thank you.
Ma'am, from participants also there is a question, ma'am.
Okay, sir.
What is the difference between viscous fluid and nanofluid?
So nanofluid, viscous fluid is a pure fluid. Nanofluid is here. So nanofluid means we add some nanoparticles. We use very small nanoparticles can be added to the flow, to the fluid, sir.
Another question, can you give one example of nanofluid? Can you give one example of nanofluid?
So nanofluid is copper. No.
What is your answer to that question, Ms. Hemavati?
Yes, ma'am.
He had asked you to give an example of a nanofluid. No, what did you say? Copper.
Copper is it's not the example of an nanofluid. I'm sorry, madam.
So you're working on nanofluid, and you should be able to tell the difference.
Yes,
No,
yes.
the viscous fluid that you have considered. Which viscous fluid are you considered here?
Water-based flow used, ma'am.
No. He had asked you a question to give just an example of a nanofluid, not even the nanofluid or the nanoparticles that you've considered. He just asked you to give an example of a nanofluid. You can give that, no? You're not able to give. Okay, what is
So
the implication of your
it is
Grashof
ceramic.
number and Inman number?
Ma'am, it is a ceramic.
What?
Ceramic.
Ceramic is an example of a nanofluid.
Yes, ma'am.
You need to read a little bit more. That's okay. Grashof, you were talking about the effect of Grashof number, no, on various fluids that you've considered.
Yes, ma'am.
What exactly is the implication of Grashof number and Brinkman number?
These are all the constants.
Yeah, I know they are constants. You have varied that and you have studied its effect. But what does it indicate? What do you mean by?
Non-dimensional numbers.
Pardon?
They are non-dimensional numbers.
So when you change that, what does it indicate actually? I know it is a constant, no non-dimensional only. Constant
Yes,
means
sir.
like that only. No, but I'm asking you, what does it indicate with respect to the fluid that you're talking about? The basic question only. I'm not asking anything in detail about the work that you've done. I'm just asking you the numbers that you've studied. What is its indication?
I don't know.
Or else I should put it this way. Why did you study those numbers, the effect of those numbers? What was the motivation of doing this? Is there an answer, or else should I wait, or you're saying no? What is it?
Yeah, madam. So I have to read.
Okay. And one more suggestion, what I would like to give for your presentation is you've just copy pasted some text in your presentation slides, but that is not the right way actually. When you're giving
Yes.
presentations, try to keep the minimal text in your slide.
Okay, ma'am.
It can be bullet points, and you can then explain what you want to, rather than
Okay.
pasting an entire paragraph. And I would
Yes.
like to just read something more on nanofluids and also these numbers which you're working on. Okay. Okay.
Okay,
All the best.
ma'am.
Yeah, yeah.
Okay, thank you, ma'am. Now I invite Ms. Aishwarya S. Sasitharan to present a paper. Aishwarya, ma'am, your screen not visible, ma'am.
Okay. Okay.
Yes, ma'am.
Is it visible now?
Yes, ma'am. Now visible.
Okay.
Okay, ma'am. You can continue.
Good afternoon, all. Myself, Aishwarya S. Shashidharan, research scholar under the guidance of Dr. Sabu MC, St. Albert's College, Ernakulam. And the topic of my paper is General Solution to Einstein's Field Equation for Vaidya-Tikekar Metric. Well, to begin with, let's look at general relativity and Einstein's field equations. General relativity is a theory of space and time. It establishes a correspondence between matter energy and the geometry of physical free space, the presence of the former inducing a curvature in the latter. Einstein's field equation constitute a highly nonlinear system of second-order partial differential equations which relate the 10 metric coefficients to physical variables with 4 space-time coordinates as independent variables. And Einstein's field equations are usually used in the study of strong gravitational fields such as superdense stars. So my paper is mainly based on superdense stars, and hence in order to study about superdense stars, say for example about neutron stars or black holes, it's very essential to solve Einstein's field equations. Vaidya and Tikekar had done the same using relativistic star models. So initially we are looking at the Vaidya-Tikekar approach, what they have done. So they have used a spherically symmetric spacetime metric, and this is the metric that they have used. Here we know that the only variable that is k. K is a variable, and k is actually the spacetime in the interior of a spherical distribution of mass at rest. And k is denoted by 1 minus b square by r square, where capital R denotes the solar radius. For this, they have used a tensor Tij, which is given by this equation, and a unit for velocity. It's just an approach what they have used. In the next slide, we are looking at the Einstein's field equation. So our whole aim is to solve Einstein's field equation, and we are looking at what Vaidya Tikekar have done and what else we could do. So Einstein's field equation is Rij minus half into Rgij equals 8 pi g by c square into Tij, where Rij denotes the receipt tensor, capital R denotes the receipt scalar, and Tij denotes the energy momentum tensor. The small gij, it plays the role of potentials for the gravitational field. I think rest all constants are very much familiar. Capital G denotes the universal gravitational constant, and small c denotes the velocity of velocity of light. So by substituting this Einstein's field equation in our spacetime metric, which we have defined previously, we could end up in 3 equations. So these are the 3 equations. Actually, Einstein's field equation is a set of 10 to 12 nonlinear second order partial differential equations. But after substituting this Einstein's field equation into our space metric, we derive these 3 equations. And equation 4, from the equation we can see that it relates density. This rho denotes density and the radius. So equation 4 shows that the density of the fluid is determined by the curvature of the physical free space, and equation 5 actually denotes pressure. Small p denotes pressure. Equation 5 gives the variation of pressure with rate small r when nu is chosen as it satisfies equation number 6. So these are the 3 equations that we have got. And what they have done is they have defined some new variables, psi and z square. And after substituting these in our previous equation, it end up like this. And they have again defined an independent variable u square, which is capital K by k minus 1 into z square, giving the condition that k need to be less than 0. This is very important. K need to be less than 0. Our previous equation becomes this. It's very well clear that this equation represents a second order nonlinear differential equation. And for solving this, they have used a recurrence relation considering psi equals sigma ak uk. After substituting this summation into our previous differential equation, it ends up in a recurrence relation. In order to solve this, we have to put n square minus 2n plus k minus 1 equals 0. But we know that the small n are actually natural numbers. The small n denotes natural numbers. In recurrence relations, the small n denotes natural numbers. And our aim is to find the value of capital K. And what we could find here is, it can be verified that previously we have noted that our k need to be less than 0. So our k need to be negative. That's the assumption we have taken. So it can be verified that if k is to be in the range of k less than 0, the simplest value of k should be minus 2, which corresponds to n equals 3. So when you substitute n equals 0, our k will be positive. When you substitute n equals 1, also k will be positive. So the smallest value of n is 3, and we get k to be minus 2. Similarly, when you put the next value for n, you will get different values of k. So the only problem with this Vaidya-Tikekar solution was that it is not applicable for any value of k. It is only applicable for particular values of k. That means we could get the solution of Einstein's field equation only for particular values of k. So we cannot generalize it as a whole. I mean, like not for all values of k. So this was the limitation of Vaidya-Tikekar model, and there comes the importance of our model. So what we have done in our paper is we have derived a general solution for Einstein's field equation, which is very important in today's research field, as many scientists are working in Einstein's field equation and solving this, doing research. So for that, what we have done is we have defined a new independent variable x, which is equal to u square, and this makes our previous equation to a hypergeometric form. This is the hypergeometric form, and after solving this hypergeometric equation, we could get, this is the final solution. A into f function, b x raised to half into another function. This f of something, f of abcx, this is of that form. This is actually the hypergeometric function where capital A and capital B are arbitrary constant. So this is our general solution to Einstein's field equation using the same metric or using the same modeling techniques as what Vaidya and Tikekar have used, and we could get a general solution which is applicable for any value of k. K need to be negative, but it is applicable for all values of k, whether it be natural number, whether it be integral, rational, any values of k, this equation holds. Since these fluid solution of Einstein's field equations were obtained without, so these are the boundary conditions that we have used, and we should notice that when we have defined a metric previously, that metric was defined for the interior of the spheroidal space that we have considered, and exterior is usually defined by the Schwarzschild's exterior metric. And since at the boundary there occurs a continuity, so this should be equal with our metric, and that helps us to derive values for our capital A, capital B, these constants. This is the first boundary condition. Next is across the boundary R equals A, our pressure will be 0. That means pressure is 0 at the boundary, and the mass density rho and the fluid pressure should be positive within the configuration. Inside the configuration it's positive, and it keeps decreasing towards the boundary. That means it's maximum at the center and it keeps decreasing towards the boundary. That is what the fourth condition says. The gradients dp by dr and d rho by dr should be negative, and dp by d rho should be less than 1. So these are the boundary condition. After substituting these boundary conditions into our solution, we could get few conditions. And the last condition says that this is the only one constraint that we have in the value of k, that our k value should be less than minus 3 by 17. So you can consider any value of k for this. Yes.
Ma'am, already 8 minutes more, ma'am. So
okay.
Conclusion.
Yes. So this is the only constraint that we are having is k need to be less than minus 3 by 17, and k can take any values less than this. Physical plausibility and boundary condition is evaluated for a particular value of k equals minus 1. This is also very well done in our paper, but I'm not mentioning it here. But in order to check the conditions, this is also done. That's it. Thank you.
Any question from the participants?
I will check, ma'am. I think there is one question, ma'am. If k is greater than or equal to 0, then what will be happen? Is there any study on this k value?
I'm sorry that I had a connection issue. Can you repeat?
I will read the question, ma'am. I will repeat, ma'am. If k is greater than or equal to 1, then what will be happened? Is there any study on this k value? Shall I repeat the question, ma'am? If k is greater than or equal to 0, then what will be happened? Is there any study on this k value?
K is actually the oplateness of the space. Oplateness in the sense, what do you say? I mean, we are defining actually spheroidal space. Spheroidal in the sense, a four-dimensional space which looks like a sphere. Sphere is in 3D. So if you take it to the next level as a four-dimensional space, that is called spheroidal. And K actually defines the oplateness. What do you mean? Oplateness means the bulging sort of thing. So if k becomes negative, I mean k becomes positive, it's not actually a spheroidal, it becomes pseudospheroidal. Pseudospheroidal means something, something of the shape of a torus. Actually, what we are doing here is we are looking at superdense stars like neutron stars, black holes, and all. Our whole aim, our ultimate aim is to check whether, check the upper limit that a neutron star can have, upper limit of mass that a neutron star can have. So we are looking at certain objects which has the shape of a spheroidal. So for that, k need to be negative. If k becomes positive or zero, it actually changes its shape. It will not be, it will no more a spheroidal shape. So this is the assumption that we are taking. If k is positive, it becomes, it is pseudospheroidal. It is pseudospheroidal.
Okay, ma'am.
So in our
One
assumptions,
more
we are
question.
taking k to be less than 0.
Okay,
I
ma'am.
hope
Ma'am,
it's
one more
clear.
question, ma'am. One more question, ma'am.
Yes.
Is your solution approximate or exact?
Okay.
If is it approximately means what will be the order of convergence? Is your solution approximate or
Actually,
exact?
hypergeometric solution.
Okay.
So for hypergeometric solution, I can say it's a closed form solution. Closed form in the sense, it's an infinite series, but we are converging it to a closed form. It's hypergeometric solution. So how shall we say about convergence? I mean, it's an infinite series, but we are taken it in a closed form. It's not exact. It cannot be exact because we are using modeling techniques to solve, and all these are done on certain metric that we have done. So it cannot be an exact value as such.
Okay, ma'am, can you just tell me
First
how
of
do you
all, we
fix
are
the
looking
boundary
at
conditions for your problem?
Boundary conditions. Actually, can I go back to my slide? I think, is it possible?
Yeah. That would be nice.
Okay. Is the slide visible, ma'am?
Yeah.
Okay. 1 second, ma'am.
For me, I don't know for others whether it would have been, the screen was not so
Yes,
visible. No? Clear.
yes, ma'am. Visible, ma'am. Screen visible, ma'am. But
Screen visible, but it's not clear. No?
yes, ma'am. Not clear, ma'am. Because
Not
of
clear.
network.
Throughout the
Yes,
presentation,
ma'am.
it was not clear actually. So we were not
Yeah.
actually able to see all the equations clearly.
Ma'am, network poor connection, ma'am.
Maybe,
So we got.
maybe at your end, no, network connection is poor. So I
Yes,
thought
ma'am.
it was a problem here, but it's not a problem here. That's what I
But-
understand.
Oh, I'm really sorry.
No, that is okay. We are
I
all
was not
now
aware of it.
okay with this.
But
No, we know
are
that
you
this
able to see
happened.
it now? Now also is the problem? Okay. So, ma'am, in between, while we are deriving while we are substituting this Einstein's equation into our metric, we got 3 equations. So, in the first equation, it actually relates between our density and radius.
Yeah.
So, from that, we could see that the radius, the density is maximum at the center. That means when you put r equals 0, when you put the radius equals 0, the density happens to be the maximum.
Yeah.
And once it goes to the boundary, it keeps on decreasing. So that was our one boundary condition. That is, it keeps on decreasing. That means dou by dou r is negative. Similarly, we have derived the boundary condition.
Okay.
Okay, thank you, ma'am.
Go to the next presentation.
Okay, ma'am. Now I invite.
Thank you so much. Thank you so much.
Okay. Thank you, ma'am. Thank you, ma'am. Now I invite Mr. Akmal Rasa to present a paper.
Hello.
Sir, you can no need
Am I
to
audible
unmute
to you?
your video, sir. No need to unmute your video, sir.
Okay,
Your
okay.
video also. Okay.
I mute this because the quality of the should not be very. Shall I start now?
Okay. You can continue.
Is it visible?
Yeah, visible.
Okay.
Full. Actually, it's in
Let
full
me.
screen or
Yeah,
full
I am doing.
screen. Just press F5. Okay. Now okay. You can continue.
Good evening, everyone. My name is Akmal Raza. I am PhD student at Department of Mathematics, Jamia Millia Islamia. Today, I am here to present my paper entitled Approximation of Singularly Perturbed Differential Difference Equation using Haar-Wavelet Collocation Method. In this paper, we solved perturbation problem which occurs delay, and there are two types of singularly perturbed differential difference equation. We solved this problem using wavelets. Here in this paper, we discuss first wavelet and Haar-Wavelet, and we discuss in the second section singularly perturbed problems, and in the third section we discuss the solution. So I'm going to start. Wavelets are the square integrable function. Any square integrable function is said to be a wavelet if it satisfies an admissibility condition, which is given here. I am highlighting that if you can visit. So integration over R psi cap omega square upon mod omega dt should be finite. Here psi cap is the Fourier transform of psi. And now the another definition of wavelet transform. So wavelet transform of a function ft can be given by this formula WAB of f equal to integration ft 1 upon square root mod a psi star t minus b upon a dt. Here psi star is the complex conjugate of psi, and the inverse wavelet transform of f can be calculated by the following equation: ft equal to 1 upon c double integration of WABF psi ab dt, which is a wavelet transform. Here c can be found by this equation, integration of psi t square upon omega mod omega dt. Now Haar-Wavelet. Here we define Haar-Wavelet. Haar-Wavelet is defined in equation number 1 by HIT. HIT is 1 when t lies between xi1 to xi2, and HIT is minus 1 when t lies between xi2 to xi3. Here xi1 is given by k upon m, and xi2 is given by k plus 0.5 upon m, and xi3 is given by k plus 1 upon m. I am highlighting this so you can see this. And this I is the wavelet number. So you can calculate this I wavelet number by this formula. I equal to m plus k plus 1, and m depends upon j. J is the resolution level, and when HIT, this is true for I is greater than 2. For I equal to 1, the Haar-Wavelet is given by equation number 2. Now on integrating equation number 1, we will get the equation number 3, which is the integration of the Haar-Wavelet. Again integrating this equation number 3, we will get the double integration of the Haar-Wavelet, which is given by equation number 4, which is Qt equal to this. And in similar manner, the nth integration of the Haar-Wavelet is given in equation number 5. Now, a multi-resolution analysis consists of a sequence of subspaces Vj, which are closed subspace of L to R. These Vj satisfies, if these Vj satisfy these following condition, that is increasing density, separation, scaling at orthonormal basis, then we can say that Vj spaces are said to be a form a multi-resolution analysis for the wavelet space. And any square integral function f can be approximated by equation number 6, which is given in equation number 6. Here I am highlighting this. Ft equal to summation I equal to 1 to n ai hit. Here ai are the unknown coefficients, and hit is given in the previous case as Haar-Wavelet. And these ai can be calculated by equation number 7, and we calculated the collocation point xu by equation number 8. Here we describe the Haar-Wavelet matrix and the integration of the Haar-Wavelet matrix, and the second order a double integration Haar matrix as H, P and Q for 8 points. Now I am going to start the singularly perturbed differential difference equation. There are various applications of these equations. Here we describe first kind of differential difference singularly perturbed equations in equation number 9. This I highlighted it. Why we are calling it a singularly perturbed delay differential equation? Because epsilon is a perturbation parameter, and this t minus delta is the delay term containing with derivative. That's why we are calling it singularly perturbed delay differential difference equation. And the second kind of this equation is known as the singularly perturbed convection delay dominated diffusion equation, which is given in the next equation, in equation number 10. In this problem, you can see that the delay term is in with y. The delay term is with y. and the previous equation, the delay term is with derivative. So if the delay term is with y, then this type of problem are said to be a convection delay dominated diffusion equation. Now in this section, we solve the linear singularly perturbed delay differential equation. To solve this kind of singularly perturbed delay differential equation, we approximated the delay term by Taylor series. Here, you can see in the equation number 12, we approximated it by Taylor series, and with the help of equation number 12 and 11, we obtain equation number 13, which is a singular perturbation boundary value problem. And here above we have given the boundary values. Now we will solve this problem by Haar wavelet. To solve this problem 13, we assume that y double derivative is an approximation summation I equal to 1 ai hit. Now integrating this equation 14, we will get y dash t, and again integrating this 15, we will get yt. So we obtain y dash and y double dash here, y dash in equation number 19 and 18, and then put these equation number 14, 18 and 19 in equation number 13, we will obtain the system of linear equation. While putting these value y dash and y double dash in highlighted equation 13, we will get this system equation number 20. This is I am highlighting. So we obtain this system of equations. Here in this system of equation, ai Haar wavelet are unknown. So we can solve this equation ax equal to b. It is a system like ax equal to b, and we can find x by a inverse b and obtain ai unknown coefficients, which are Haar wavelet coefficients. After calculating these ai unknown coefficients, we can put them in equation number 19. This here in equation number 19, I am highlighting it again. In this equation, after calculating ai, we put them in equation number 19, which is an approximate solution of the singularly perturbed boundary value problem or singularly perturbed delay differential equations. Now in this section, we solved this non-linear singularly perturbed differential difference equations. To solve this singularly perturbed non-linear system, we applied the same method, but in this case we will obtain the non-linear system. So to solve this non-linear system, we apply Newton's method and solve again as in previous case. We will get the solution of non-linear singularly perturbed differential difference equation. Now in this section, we solved singularly perturbed convection delay dominated diffusion equation. So we discuss when the delay term occur in y, then this problem is singularly perturbed convection delay dominated diffusion equation. Again, to reduce this delay term, we use Taylor series method here in equation number 25 and retarded this term by with the help of equation number 25 and 24, we obtain this equation number 26. Here I am highlighting again it. To solve this equation number 26, we again assume that y double derivative is equal to summation I equal to 1 to n ai hit, and again integrating this equation, we obtain y dash and y here. We get y here in equation number 32 and y dash here in equation number 31. Now put these values from equation number 32, 31 and 27 in this equation 26. On putting this value, we will get this system of equations. This system of equation 33. Now again we can find out the unknown coefficients ai and put them in equation number 32. It will be the approximate solution for the singularly perturbed convection delay dominated diffusion equation. And similarly, we can solve the nonlinear singularly perturbed convection delay dominated diffusion equation, and again in this case we will get the nonlinear system, and in this nonlinear system is solved by Newton method, and we can get the ai coefficients, unknown Haar wavelet coefficient, and put them in equation number 32 and get the solution of nonlinear system of nonlinear singularly perturbed convection delay dominated diffusion equation. Here we discuss the convergence analysis of the proposed method.
Sir, sorry to disturb you. Already 8
Yeah,
minutes
I'm going
more.
to conclude.
Okay.
Yeah, here because we do not have the exact solution, so we calculated the maximum absolute error by equation number 32, 38, and in case of singularly perturbed convection delay dominated diffusion equation, we calculated the maximum absolute error by equation number 39. Here we discuss the example. You can see I solved this example linear with the help of Haar wavelet. Here we have the exact solution and compare the solution with the exact solution. We obtain the maximum absolute error up to 10 to the power minus 6. And we compared our result with uniformly method and spline method and other method. Here we solve a non-linear problem. And example 3, we solved singularly perturbed convection delay dominated diffusion equation, and we compared our solution with the asymptotic solution and other method discussed in literature. Here are maximum absolute error obtained by Haar wavelet in MATLAB. This is the solution and exact solution. Here we discuss non-linear singularly perturbed convection delay dominated diffusion equation, and these are maximum absolute error. These are some references. Thank you.
Sir, any questions? Sir, one more. Can you give any interesting properties of Haar wavelet matrices?
Yeah, Haar wavelet is symmetric, orthogonal, and one of the most property of the Haar wavelet is compactly supported. That's why we can solve every kind of differential equation, that is delay and ordinary differential equation or partial differential equation, or you can solve also fractional differential equation using these wavelets. Because of the lack of timing, I did not discuss the all properties of the Haar wavelet. Here, I have discussed it. Any other doubt?
One more question is that, wait.
Yeah.
Okay, where Haar wavelet transform is defined? I mean, in which domain it is defined?
I can see. Mr. G. Kumar comment. Yeah, I can show you. Here, I defined the wavelet transform. This definition: WAB of f integration ft 1 upon under root square 1 upon mod of square root a psi star t minus b upon. Here, psi star can be used as a Haar wavelet. This H1T can be used as Haar wavelet in this property. We do not make the Haar wavelet transform, but we generalize only, we define wavelet transform. In case of Haar wavelet transform, we can put Haar wavelet in terms of psi. I hope you can understand me what I am trying to say.
I think one more question.
Yeah. I'm really happy to answer.
Okay, I think no questions. Sir, any other questions, sir? Ma'am. Okay.
Yeah. See, for approximation, you use the what do you say, the MATLAB only?
Yes, ma'am. I used MATLAB.
Okay. Thank you.
No more question?
No.
From audience, ma'am, from audience, one more question, ma'am.
Can this wavelet be used for convection modulation?
Actually, I do not have the knowledge of convection modulation, but wavelet are very useful in every area. In image processing, also signal processing, every area of application, you can use the wavelet. People are still using the wavelet in cryptography and network processing, image compressing, data processing, cloud computing.
I think these are the number of questions. Thank you. I think we can go to the next presentation, sir.
Ma'am, today only 5%, ma'am. 1% cannot join, ma'am, due to some network issue, ma'am. TN Misra, he cannot join, ma'am. So today
so
only,
we are done with the presentations.
yes, ma'am, only 4%, ma'am.
Okay, thank you so much. So I can leave now? Yeah.
Thank you, ma'am.
Okay, thank you so much.
Thank you, ma'am. Thank you, ma'am, for spending your valuable time in sharing your knowledge in view of motivating and encouraging students, research scholars, and teachers. Thank you, ma'am. Dear participants, we will meet tomorrow at 10 a.m. in day 3 session. Thank you.